This is Mrs. Schroeder. We're going to begin talking about Section 2 today in Chapter 2 about the scientific method, focusing on what the scientific method is and explain the difference between a hypothesis and law. In class we're going to talk a lot more about how experiments are set up, how to control conditions. We'll be spending more time in class with that. So the scientific method is a strategy used for solving problems. It doesn't mean you have to use every step, every time, but it gives us a logical course of action to follow. So good scientific experiments have a hypothesis, which must be reasonable and able to be tested. A hypothesis is sometimes called an educated guess. It needs to be a little more than a guess because we have to have some background knowledge in order to create a hypothesis. With the experiment, it must be controlled. The experiment must be set up to actually test your hypothesis that you make. And then we have to control. We have to know what variables we're going to be using and how we can keep them constant. Everything's constant except the manipulated variable. Whatever you choose to change. So, for example, if I am trying to test a fertilizer to see if plants will grow better, the variable that was changing is the fertilizer. Everything else stays the same. The amount of water, the amount of light, the type of soil, the type of plant, that all stays the same, but I'm changing the amount of fertilizer. The responding variable then is what does change in response to. So you could measure plant growth, the mass of the plant, the height of the plant, the number of leaves of the plant, the number of tomatoes it produces. In some way responding to the change of the fertilizer that you added. That becomes the responding variable. Then we draw a conclusion. It must be based on what actually happened. It may not be what you expect, and that's okay. What you need to learn in science is it's okay to be wrong. You must report what you actually did. And this rolls over into lab. If you are told to add 2 grams of something and you really measured out 2.2, it's okay. Write down 2.2. We always write down exactly what we did, not what we want to happen or what we expect to see. And then we repeat it. Because sometimes something happened that you didn't account for. Maybe when you're doing your fertilizer, you didn't realize that somebody had opened the window when you were gone and it knocked one of the plants over, and it knocked over, and they came back and tried picking it up and scraping all the dirt back into it and trying to make it look good. But really it was this thing that happened to one plant, not the other, that really screwed up the experiment. And sometimes you don't understand what those kind of things are unless you can repeat it. Can you always get this repeatable data? Does it always work? Okay, and it's not considered valid unless it works every single time. Now, discoveries are made when we start to observe things that we don't expect. A couple well-known examples of these. Teflon. The Teflon is something that we use in a lot of materials now. It's the like papery stuff and CD covers and mailing envelopes that you really can't rip it. It's also used on non-stick coating on the surface of pans and things like that. A scientist discovered this on accident. He was trying to make something else. It turned into these white flakes. He was curious what they were, what kind of properties are these. He'd never seen them before. And he realized this incredible material that he made, and he was smart enough to say, hey, I'm going to investigate further what I just made. It's not a coolant, it's not a liquid or gas coolant, but it's something really neat, and he investigated that. Another well-known example, maybe not so well-known, but a pretty important discovery, happened in 1956. Back then, coloring for clothes was very, very expensive. Most common people just had their gray or standard colors you can make from wool or from cotton that you just came. They weren't able to actually dye them. Only the royalty got these colored dresses and colored, really very nice color things. This guy was looking for a drug to make malaria, so he made this purplish stuff. And he realized that he could actually make this cheap dye and went on to sell that in England and passed on the opportunity to make colored material. One you may have not realized about is silly putty. Silly putty was made by a chemist who was trying to create a better rubber, and they found the stuff and it could bounce, and they made it into this children's toy. You can bounce it, you can stretch it, and somebody was brilliant enough to decide to try to market that as a toy. Getting back to scientific method, after you've done a lot of experiments, you come up with things called theories and laws. Now, a lot of people get really confused into theory and law, and we use the term theory and law in different contexts in our everyday language. But the scientific definition of a theory is something that attempts to explain something that always happens. But we're trying to explain why. Why does gravity work? Why did things evolve? Why do plate tectonics? Why do continents move? What is atomic theory? What do atoms look like inside? Trying to explain things that experimental results over and again have proven happen. We try to explain why. A law, on the other hand, will just describe what will happen. So, law of conservation of matter says matter is always conserved. Energy is always conserved. Gravity, if I drop a pen, it's always going to drop onto the ground. No matter how high I drop it from, no matter if I throw it first, it will drop to the ground. Law of gravity. Doesn't tell us why, but it always happens. A little more on this law of conservation of mass. We're going to use this a lot in chemistry because it really relates to atoms and to reactions and chemical processes that we use. Basically, it says that matter cannot be created or destroyed. Whether chemical change or physical change, matter is always the same. I can rearrange the atoms, I can change their state, but it doesn't matter what I do, I have the same amount. So if I have 5 grams of A, and I react that with 5 grams of B, how much am I going to end up with at the end? 10 grams, no matter what. 10 grams of product. It doesn't matter how it's arranged, if it's AB, if it's AB2, if it's something else, it's always going to be 10 grams of this material. Now, it's a law, so it doesn't explain why. It just says this is what happens. So, one way to keep track of things, or try to keep them straight in your mind, hypothesis will predict an event. I think that the mass will stay the same as a hypothesis. Theory explains it. Why? Why does it stay the same? And the law describes it. And then scientists use models often in science, because a lot of times in science things we clearly can't actually see what's happening. So we use models to describe it and to help us learn about it and to help us understand what happens. I'm going to play another little video clip here to show us what happens in models.
Models are used to represent things that are too small to see, such as atoms. Models can also represent objects in the solar system that are too large or far away to observe in certain ways. For example, this model can be used to show how the movements of the Earth, the Moon, and the Sun result in the different phases of the Moon. Scientists and engineers use computers to model systems and processes that are too expensive, complex, or dangerous to test in real life. For example, computer simulations use data related to ocean temperature and weather patterns to predict El Niño events, and decide when to evacuate citizens prior to a hurricane making landfall. Models can also be used to represent ideas, concepts, or theories. For example, scientists noted that a rolling object, such as a push lawnmower, veers when it encounters at an angle a surface that slows it down. Light similarly veers when it passes from an easy-to-go-through medium, such as air, into a thicker medium, such as water. Scientists use the lawnmower model to help explain why light might exhibit such a behavior.
So again, we use models to help us understand things. Computer-aided models are a much bigger deal than they used to be. We're going to start using some simulations and models in our class once we get our computers, and we'll be able to start seeing the power behind models. And that's all I have for this section. So for tomorrow, start looking ahead at scientific method. We're going to start thinking about how to actually design experiments and how experiments should be set up. We'll talk more about that in class. Signing off for now, this is Mrs. Schroeder.